You think you have time. That's the illusion we all live with. We wake up, we check our phones, we worry about our mortgages, our careers, our relationships. We plan vacations 5 years in advance. We get angry about traffic on the highway. We stress about quarterly earnings reports. We obsess over the drama in our personal lives. We assume the sun will rise tomorrow, and the next day, and the day after that for thousands of years to come. But scientists have just revealed something extraordinary, something that reframes everything we thought we knew about our planet's future. The sun isn't just going to die someday in the distant, almost incomprehensible future. It's going to destroy Earth far sooner than you probably think. And the science behind why is absolutely fascinating. Think about that for a moment. Everything you've ever known, every person who has ever lived, every civilization that has ever existed, all of it has occurred on a planet where the sun has always risen and set with stunning regularity. This consistency is so fundamental to human experience that we barely question it. We've built our cultures around it, our religions, our calendars. We've created timekeeping systems based on solar cycles. The day is defined by one rotation of Earth relative to the sun. The month originally tracked the lunar cycle. The year tracks Earth's orbit around the sun. The season marks the sun's position in the sky. All of these fundamental organizing principles of human civilization are based on the assumption that the sun will continue to rise and set the way it always has. This assumption is so deep, so foundational, that challenging it feels almost heretical. It feels wrong to even suggest that the sun might not always be reliable. And yet, the evidence is clear. The science is compelling. The sun is changing, and it's changing in ways that are going to profoundly alter the future of this planet. Let me start with what you think you know. Most people have heard that the sun has about 5 billion years left to live. That's the conventional wisdom you hear repeated in textbooks and documentaries. 5 billion years. Take a moment to really contemplate what that number means. 5 billion years. It's a number so large it might as well be infinity. 5 billion years ago, dinosaurs didn't exist yet. Mammals hadn't evolved. Fish were just beginning to explore the oceans. Complex multicellular life was still billions of years away from even the possibility of existing. So when we say the sun has 5 billion years remaining, our brains essentially shut down. Feels eternal. Feels safe. It feels like we're dealing with something so far in the future that it has essentially no relevance to anything we care about. The human mind is not evolved to understand timescales of billions of years. We understand years and decades and maybe centuries. We can stretch our imagination to understand thousands of years, though it's difficult. But billions of years, that's beyond our intuitive grasp. So the conventional answer, the sun has 5 billion years left, provides a kind of comfort. It says that Earth is safe. Life is safe. Whatever problems we face today, whatever challenges humanity encounters, we have essentially infinite time to solve them. But here's where the science gets interesting. And this is where most people, even educated people, even people with advanced degrees in sciences other than astronomy, get it wrong. The sun doesn't have a simple on-off switch. It doesn't burn steadily for 5 billion years and then suddenly turn off or explode or do whatever apocalyptic thing you might imagine. That's not how stars work. That's not how the sun works. The sun is, right now, at this very moment while you're watching this video, fundamentally changing. It's aging. It's not aging the way humans age, with a decline in vigor and capability and strength. Instead, it's aging in a way that makes it more powerful. It's getting hotter. And as it gets hotter, it's sending more and more energy toward Earth. This is the crucial fact. The sun is not getting dimmer as it ages. It's getting brighter. And this fact, this simple physical principle, is what's going to destroy Earth's habitability. The physics here is elegant but unforgiving. The sun is powered by nuclear fusion. This is the most fundamental fact about stellar astrophysics. And if you want to understand the sun's future, you need to understand nuclear fusion. Deep in the core of the sun, at a distance of about 400,000 miles from the sun's surface, temperatures reach about 27 million degrees Fahrenheit. Let me say that again. 27 million degrees. On the Celsius scale, that's about 15 million degrees Celsius. These numbers are so large they lose meaning. Your mind can't really grasp what that means. It's incomprehensibly hot. It's hot enough that all matter exists as plasma. Atoms are stripped of their electrons. It's hot enough that the quantum mechanical tunneling probability for hydrogen nuclei to fuse becomes significant, even though classically they should repel each other due to their positive electric charges. At these incomprehensible temperatures, two hydrogen nuclei, which are really just protons, are forced together despite the electrostatic repulsion between them. When two hydrogen nuclei fuse, they create one helium nucleus. And in that process, something remarkable happens. A tiny amount of mass converts directly into energy. This is Einstein's famous equation, E equals mc squared. The mass of two hydrogen nuclei is slightly more than the mass of one helium nucleus. That tiny difference in mass, it's only about 0.7%, gets converted entirely into energy. That energy is released in the form of heat and radiation. That's where the sun's power comes from. That's where the light that reaches Earth comes from. That's where the energy comes from that powers all of photosynthesis and all of life on Earth. But here's the crucial part that changes everything. As the sun fuses hydrogen into helium, something happens over time. The helium accumulates in the core. Year after year, billion after billion, helium is being produced in the core through nuclear fusion, and it stays there. The pressure from gravity keeps it trapped. The helium nucleus is heavier than a hydrogen nucleus, and there's nowhere for it to go. And as the core becomes progressively more full of helium and more depleted of hydrogen, something counterintuitive occurs. Something that seems backwards at first, but makes perfect sense once you think about it. The sun has to burn hotter and faster to maintain the pressure needed to support its own weight against gravity. Think about that. The sun is fighting gravity. The sun is so massive that its own weight is trying to crush it. The gravitational force is trying to compress the sun down to a point. The only thing preventing the sun from collapsing under its own weight is the pressure inside the sun pushing outward. That pressure comes from the heat of nuclear fusion. As the sun ages and accumulates helium in the core, maintaining that outward pressure becomes harder and harder. It's like if you're holding up a heavy weight and the weight keeps getting heavier, you have to push harder to support it. So the sun has to fuse faster and faster to maintain the outward pressure that counteracts gravity. This is not a small effect. It's not a minor adjustment. It's a fundamental driver of stellar evolution. It's why stars change over time. It's why the sun is different today than it was billions of years ago, and why it will be different billions of years from now. This process is not something we discovered yesterday. This is not some cutting-edge observation that just came out last week. Astrophysicists have understood the basics of stellar evolution for decades. The models of how stars are born, how they spend the majority of their lives fusing hydrogen in their cores, how they change as they age, and how they eventually die have been known since at least the 1960s. These models have been refined and improved over the decades, but the basic picture has been known for a long time. But what recent research has clarified, and this is the stunning part, is how dramatically this process will affect Earth far sooner than the conventional 5 billion year timeline suggests. Here's the crucial detail that changes everything. The sun is getting about 10% brighter every billion years. Let me repeat that because this is important. Every single billion years, the sun increases its luminosity by 10%. That might sound gradual. That might sound like a slow, imperceptible change. After all, 10% over a billion years is only a tiny fraction of a percent per year. That's basically 0.000001% per year, roughly. That's incredibly slow by any human standard. But it's not a small change. Not for a planet like Earth. Not for a biosphere that depends on a very narrow range of solar energy arriving from the sun. Consider this moment right now, as you're watching this video or reading these words. The sun sends about 1,361 watts of energy to every square meter of Earth's upper atmosphere. That's what we call the solar constant. Technically, it's called the total solar irradiance. It's actually not constant at all. It varies slightly from day to day and from year to year based on solar activity, but it's constant enough for our purposes. Let's call it roughly 1,361 watts per square meter. This amount of energy, filtered through our atmosphere, absorbed and reflected and redistributed by our weather systems, allows liquid water to exist on our planet's surface. It drives our weather. It creates the wind and the rain and the storms. It powers photosynthesis, which is the chemical reaction that converts light energy from the sun into chemical energy that plants can use to grow and build their tissues. And since all of animal life ultimately depends on plants, either directly or indirectly, every animal on Earth depends on this particular amount of solar energy. Humans depend on this. Your existence right now as a conscious being listening to or reading these words depends on this. The photosynthesis in plants feeds herbivores, which feed carnivores. Or if you're a vegetarian, the photosynthesis in plants feeds you directly. But every calorie of food energy in your body ultimately came from the sun's energy being converted by plants through photosynthesis. Now imagine that this energy increases by 10%. I know that doesn't sound like much. In the context of human experience, 10% is a small change. If your salary increased by 10%, you wouldn't think you'd gotten rich, though you'd probably be happy. If a recipe called for a cup of flour and you added 10% more, you probably wouldn't notice much difference in the final product. If your electricity bill increased by 10%, you'd probably notice it, but it wouldn't be catastrophic. But in terms of planetary climate, 10% more solar energy is not small. It's not a minor adjustment. It's absolutely catastrophic. Let me put numbers to it to make this concrete. The average global temperature on Earth right now is about 59 degrees Fahrenheit, or about 15 degrees Celsius. This temperature is determined by a careful balance between the energy we receive from the sun and the energy we radiate back into space. That balance is called the planetary energy balance. It's one of the most fundamental equations in climate science. Think of Earth as a system in equilibrium. Energy comes in from the sun. Energy goes out into space as infrared radiation. If the energy in equals the energy out, then the temperature stays constant. If more energy comes in than goes out, then the planet accumulates energy and gets hotter. If more energy goes out than comes in, then the planet loses energy and gets colder. Most of Earth's energy comes from the sun. A tiny amount comes from Earth's internal heat, the heat left over from when Earth was formed 4.5 billion years ago, plus the heat generated by radioactive decay of elements in Earth's interior. But this internal heat is negligible compared to the sun's energy. The sun dominates. So when you increase the amount of energy coming in from the sun by 10%, that balance gets disrupted. The planet can't radiate away the energy as fast as it's receiving it. So the planet accumulates heat. The planet warms. The temperature increases. And here's the important part. The planet doesn't warm linearly. When you increase solar input, that balance doesn't shift smoothly and gradually in one direction. Instead, the warming triggers a series of feedback mechanisms. These feedbacks amplify the initial warming and accelerate the heating. This is not speculative. This is not a hypothesis that we're testing. This is something we can observe happening right now on Earth. The warming caused by human emissions of carbon dioxide is being amplified by these exact feedback mechanisms. As the planet warms, more water evaporates from the oceans. Water vapor is a greenhouse gas. Actually, it's the most abundant greenhouse gas in our atmosphere. It's responsible for about 50% of the natural greenhouse effect. The rest comes from carbon dioxide, about 20%, methane, nitrous oxide, and other gases. But water vapor is the dominant greenhouse gas. So when more water evaporates from the oceans, more water vapor goes into the atmosphere. More water vapor means more heat is trapped in the atmosphere. More heat means the planet warms more. And more warming means more evaporation. This is called a positive feedback loop. It's a vicious cycle where the warming triggers a mechanism that causes more warming, which triggers more of the mechanism which causes even more warming. The effect compounds. Additionally, as the planet warms, ice melts. Ice is highly reflective. Scientists call this reflectivity the albedo of a surface. White ice has a high albedo. It reflects a lot of sunlight. When ice melts, whether it's sea ice in the Arctic Ocean, or glaciers on land, or ice sheets in Greenland or Antarctica, it's replaced by darker water or darker rock. Dark surfaces absorb more of the sun's energy instead of reflecting it away. This absorbed heat is then trapped in the atmosphere due to the greenhouse effect, causing more warming. And more warming causes more ice to melt. This is the ice albedo feedback, and it's one of the most powerful mechanisms that can drive climate change. There are other feedbacks too. There's the lapse rate feedback, which has to do with how temperature changes with altitude in the atmosphere. There's the cloud feedback, which is actually more complex and can go either way depending on what kind of clouds form. Low clouds tend to reflect sunlight and cool the planet, while high clouds tend to trap heat and warm the planet. But the water vapor feedback and the ice albedo feedback are the dominant positive feedbacks, the ones that amplify warming. And they're both powerful. For most of Earth's history, negative feedbacks have dominated. These are feedbacks that dampen changes. One example is the carbon dioxide feedback. When temperatures increase, plants can grow faster. They photosynthesize more actively. They absorb more carbon dioxide from the atmosphere. This removes CO2 from the air and reduces the greenhouse effect, limiting further warming. This is a negative feedback that acts to stabilize the climate. Another negative feedback involves rock weathering. When the planet is warmer, the chemical weathering of rocks happens faster. This process consumes carbon dioxide from the atmosphere, removing it and reducing the greenhouse effect. This too is a negative feedback that acts to stabilize climate. For most of Earth's history, these negative feedbacks have kept the planet's climate relatively stable, at least on human timescales. This is one of the main reasons Earth has maintained liquid water and habitable conditions for billions of years. The climate system has been self-correcting. If the planet started to warm too much, negative feedbacks would activate and bring the temperature back down. If the planet started to cool too much, other negative feedbacks would activate and bring the temperature back up. But as the sun gets brighter and sends more and more energy to Earth, something changes. As solar input increases, the positive feedbacks start to dominate. The water vapor feedback becomes stronger than the negative feedbacks that would normally limit warming. The ice albedo feedback becomes more pronounced. The planet enters a regime where positive feedbacks overwhelm negative feedbacks, and temperature starts to rise rapidly. This is not gradual. This is a dramatic shift in behavior. This change in the balance of feedbacks is one of the key insights of climate science. And it's one of the reasons that Earth will transition from habitable to uninhabitable, not over billions of years of slow, gradual decline, but over a relatively short period once the tipping point is crossed. Scientists have recently modeled what happens to Earth as the sun's luminosity increases over time, incorporating all of these feedback mechanisms, all of the complex physics of the climate system, all of the chemistry of the atmosphere and the oceans. And the results are sobering. About 1 billion years from now, and I know that's still an enormous time frame, but stay with me, the sun will be roughly 10% brighter than it is today. At that point, according to these models, Earth's oceans will begin to evaporate significantly. The planet will warm beyond what our current biosphere can tolerate. Most complex life will be gone. Not because of some catastrophic impact from a giant asteroid colliding with Earth. Not because of a massive volcanic eruption that blocks out the sun and plunges the world into darkness. Not because of some unpredictable disaster that strikes suddenly. But simply because the planet will become too hot for life as we know it. The temperature will rise beyond the range that the vast majority of organisms can survive. The chemistry of life will become impossible. It will happen slowly from a human perspective over millions of years. But from a cosmic perspective, it will be relatively rapid. Think about what that means. Dinosaurs existed for 160 million years. That's a long time. They dominated Earth's ecosystems for most of that period. And then in a cosmic instant, a 65 million year blink, they went extinct. Most paleontologists believe they were killed by a massive asteroid impact, though volcanic activity and climate change probably contributed. But the point is that 160 million years is a long evolutionary history. That's a long period of dominance. And yet it's only 1/6 of the time until Earth becomes uninhabitable. Humans have existed as a species for maybe 300,000 years. Our entire species history is less than 1% of a million years. Anatomically, modern humans have existed for about 100,000 years. Our species has developed agriculture in the last 10,000 years. We've developed cities and civilization in the last 5,000 years. We've developed industrial technology in the last 300 years. We've developed computers and the internet in the last 50 years. The entire arc of human technological development has occurred in an incredibly short period of time. And we have 1 billion years until the sun makes Earth uninhabitable. That's 3 million times the length of human civilization. 3 million times. The sun doesn't just get brighter at a constant rate. As it gets hotter, its core contracts and heats up even more, causing it to fuse hydrogen faster. This process accelerates. It's not a smooth, linear increase. There are inflection points. There are moments where the acceleration compounds. The warming accelerates the brightness increase, which accelerates the warming further. It's a positive feedback loop. One of these critical inflection points happens roughly between now and 1 billion years from now. Specifically, around 700 million to 1 billion years from now, something called the moist greenhouse effect will begin to dominate Earth's atmosphere. This is not a poetic term. This is not something that scientists made up to sound dramatic. This is a specific climate state that has been identified through detailed, rigorous scientific modeling. It's been published in peer-reviewed scientific journals. It's been discussed at scientific conferences around the world. It's something that the astrophysical and climate science communities take very seriously. Here's how it works. As the sun brightens, more water evaporates from the oceans. Normally, when water evaporates, it rises into the atmosphere as water vapor. As it rises, it enters progressively cooler air. When the water vapor cools, it condenses into liquid water droplets or ice crystals. These droplets and crystals form clouds. These clouds reflect some sunlight back to space and trap heat. But eventually, the water falls back to Earth as precipitation, rain, or snow. This is the water cycle that has been going on for billions of years. This cycle is beautiful in its balance. The cycle moves energy from the surface to the upper atmosphere. The cycle redistributes water around the planet. The cycle is essential for Earth's climate regulation. Without it, the planet would be very different. But this cycle depends on a crucial detail. The upper atmosphere is significantly cooler than the lower atmosphere. When water vapor rises into the upper atmosphere, it encounters lower temperatures. At lower temperatures, the air cannot hold as much water vapor. There's a limit to how much water vapor air can hold at a given temperature. This limit is called the saturation vapor pressure. When the air is saturated, water vapor condenses. But now imagine a scenario where the entire atmosphere is so warm that even the upper atmosphere is at temperatures where it can hold enormous amounts of water vapor. In that case, water vapor doesn't condense. It just keeps rising. It just keeps accumulating in the upper atmosphere. This is what happens in the moist greenhouse state. As the sun gets brighter and the planet warms, the entire atmospheric column warms. Even the upper atmosphere, even the stratosphere, becomes warmer. When this happens, the saturation vapor pressure, the maximum amount of water vapor the air can hold, increases everywhere in the atmosphere. At the same time, the rate of evaporation from the oceans increases dramatically. Warmer oceans evaporate more water. More water evaporates from lakes and rivers and vegetation. The amount of water vapor being added to the atmosphere increases rapidly. There's a critical temperature, somewhere around 85 to 100 degrees Fahrenheit at the surface, though the exact value depends on complex details of atmospheric structure, beyond which the rate of evaporation exceeds the ability of the condensation mechanism to remove water from the atmosphere. When this happens, water vapor accumulates in the upper atmosphere. The atmosphere becomes supersaturated with water vapor in the upper layers. This is a profoundly different state from today's Earth. In today's Earth, water vapor is carefully balanced. Water evaporates from the oceans and atmosphere, condenses into clouds, and precipitates back. The residence time of water in the atmosphere is only about 10 days. Water spends about 10 days in the atmosphere before falling back to the surface. But in the moist greenhouse state, water vapor becomes abundant and persistent in the upper atmosphere. The atmosphere is thick with water vapor. And at the edge of space, ultraviolet radiation from the sun breaks down water molecules directly. This process is called photodissociation. When UV photons hit water molecules, they break the bonds. The water molecule is split apart into hydrogen and oxygen. When hydrogen atoms are liberated from water molecules, they're very light. Gravity can barely hold them. Some of them are moving fast enough to reach escape velocity. They fly off into space. They leave the planet. Once hydrogen escapes to space, it's gone. It's not coming back. Not for billions of years at least. Over millions of years in the moist greenhouse state, the oceans don't just heat up. They don't gradually evaporate and then condense somewhere else on the planet in some new equilibrium. Instead, they gradually disappear. The water leaves the planet. Once the water is gone, it's gone. It's not coming back. Once the oceans are gone, something terrible happens. Something that is incompatible with life as we understand it. Life needs water. Not just any water. Liquid water. Most of Earth's life, from the smallest microbes to the largest whales, depends on liquid water. Water is not just important for life because it's one of the chemicals that life uses. Water is crucial because it's the fundamental solvent of life. It's the medium in which all biochemistry happens. All chemical reactions that constitute life happen in water. Proteins are floating in water. Enzymes are catalyzing reactions in water. DNA is being replicated in water. Nutrients are being transported in water. Waste products are being removed in water. Every cell in your body is mostly water. 70% of your body mass is water. This is not an accident. This is not something that could be changed through evolution. This is a fundamental necessity of chemistry. Water has unique properties. It's a polar solvent, which means it can dissolve a huge range of chemical compounds. It can stabilize complex molecules like proteins and DNA. It can transport nutrients and waste products through living organisms. It participates directly in many biochemical reactions. The chemistry of life is literally impossible without liquid water. Without liquid water, the chemistry of life becomes impossible. Biochemical reactions that occur routinely in aqueous environments can't occur in dry air or in a dense carbon dioxide atmosphere. It's not that life is fragile and dies easily when conditions become harsh. It's not that life has evolved to be dependent on liquid water and could theoretically evolve to be independent. It's that life is a chemical phenomenon at its core, and the chemistry that life depends on absolutely requires water as the fundamental solvent and medium. Life without water is not just difficult. Life without water is impossible. So when the oceans evaporate, life doesn't just struggle and gradually go extinct. What happens is more abrupt and more final. Life becomes impossible. The chemistry can't happen. It's not a gradual slow decline where populations shrink and biodiversity decreases and species go extinct one by one over millions of years. It's a switch, a threshold. On one side of the threshold, you have a planet with oceans and life. On the other side, you have a dead world. This is what would happen on Earth if we reach the moist greenhouse threshold and cross it. The oceans evaporate. Life vanishes. The planet becomes a dead world. And this could happen in 700 million to 1 billion years. Not 5 billion years. Not some incomprehensibly distant future that has no meaning to us. A future that's 5 times closer than most people think. A future that's closer than the time it took for dinosaurs to rule the Earth to present day. For billion years ago, the sun was about 30% dimmer than it is today. This is not a theoretical hypothesis. This is a constraint that comes directly from the models of stellar evolution. We can calculate how much hydrogen the sun has fused since its formation. We can calculate exactly how much brighter it has gotten as a result. The calculation is straightforward and well confirmed. For billion years ago, the sun was definitely dimmer. Yet the evidence strongly suggests that Earth had liquid water on its surface 4 billion years ago. We find evidence of chemical weathering that requires liquid water. We find sedimentary rocks that appear to have been formed in the presence of water. The isotopic composition of ancient rocks suggests the presence of liquid water. Moreover, life appears to have emerged very early. The oldest chemical signatures that might indicate the presence of life date back about 3.8 billion years, possibly even 4.1 billion years if controversial interpretations of certain carbon isotopes are correct. If life did emerge that early, it would have required liquid water. Life needs liquid water. So we have a paradox. How could Earth have had liquid water and life when the sun was 30% dimmer? According to our models, a 30% dimmer sun should have resulted in an Earth that was completely frozen, like a snowball. How could liquid water exist on a frozen planet? The resolution to this paradox is that Earth's atmosphere was different. It was very different. It had a much stronger greenhouse effect. There was more carbon dioxide in the atmosphere. There might have been more methane. There might have been other greenhouse gases that we don't even have concentrated in the atmosphere today. These greenhouse gases trapped more heat, compensating for the dimmer sun. This is actually a beautiful example of negative feedback in action. As the sun got brighter, Earth's atmosphere gradually lost greenhouse gases. The carbon dioxide was removed through various processes. It was incorporated into rocks through chemical weathering. It was incorporated into living organisms through photosynthesis. It was dissolved in the oceans and incorporated into shells and skeletons of sea creatures. Massive deposits of limestone formed from the shells of organisms, and this limestone locked up carbon dioxide. As the greenhouse effect weakened, the planet stayed approximately the same temperature despite the sun getting brighter. The two effects balanced out. It's like if you're slowly turning up the heat in a room, but at the same time, you're opening windows to let cool air in. The two effects can balance out, keeping the temperature relatively constant. This is called the Goldilocks principle in some contexts. Earth's climate was neither too hot nor too cold, but just right, and this was maintained despite the sun getting brighter. It's a remarkable example of how the climate system can self-regulate to maintain habitability. But this balance could not be maintained forever. The negative feedbacks that kept Earth at a stable temperature could only work within a certain range. Once the sun got bright enough, once enough greenhouse gases had been removed from the atmosphere, the negative feedbacks became overwhelmed by positive feedbacks. Once the sun got bright enough, the balance broke down. The question is, when does this happen? When does the critical threshold get crossed? When does negative feedback give way to positive feedback? Based on current models, incorporating our best understanding of climate physics and stellar evolution, this happens in roughly 1 billion years. At that point, Earth's climate can no longer be stabilized by the natural negative feedbacks. The positive feedbacks take over. The moist greenhouse effect dominates. The oceans start to evaporate. Water leaves the planet, and life comes to an end. The irony is that Earth's biosphere was essential for maintaining Earth's habitability during the early stages of the sun's brightening. Life removed carbon dioxide from the atmosphere through photosynthesis. Without life, without these processes, the greenhouse effect would have been too strong, and Earth would have been too hot for life to emerge. Life created the conditions that allowed more life to flourish. This is a beautiful example of life shaping its environment in a way that enables more life to exist. But eventually, this feedback reaches its limit. Life cannot keep the planet cool forever. The sun gets too bright. The negative feedbacks are overwhelmed. Life is destroyed by the very success of the life that came before it. For the first few 100 million years, the changes are relatively gradual. The sun brightens by a few percent. The planet warms, but the biosphere adapts. Species migrate toward the poles or to higher elevations seeking cooler climates. Evolution accelerates. New species emerge that are better adapted to warmer conditions. Biodiversity changes, but life persists. The tropical regions of Earth become less habitable. The equator becomes too hot for much of current tropical life. The poles warm significantly. The Arctic ice melts. Antarctica loses much of its ice coverage. Sea level rises as glaciers and ice sheets melt. Coastal cities and low-lying areas are inundated by rising seas. Islands disappear, but inland areas at higher latitudes might still be habitable. Life concentrates toward the poles. The habitable zone for complex life moves northward. The boreal forests expand toward the Arctic. Animals migrate or evolve to tolerate heat. Plants evolve deeper roots to find water in drying soils. Insects develop resistance to heat. Life is resilient. It adapts. But as we continue forward and the sun gets even brighter, things accelerate. Around 700 million to 1 billion years from now, the tipping point is approached. The moist greenhouse threshold is being approached. The climate system senses the boundary condition changing. Water vapor in the upper atmosphere starts to increase. At this point, the rate of change accelerates dramatically. The feedback loops amplify. The temperature rises faster and faster. Within a few million years, the climate shifts rapidly. The moist greenhouse dominates. Water vapor accumulates in the upper atmosphere. Ultraviolet radiation breaks apart water molecules. Hydrogen escapes to space. From the perspective of life on Earth, this would be a catastrophe unfolding in slow motion. Initially, life might seem to adapt. New species emerge that are heat-tolerant. Some organisms might even thrive in the warmer environment, at least temporarily. Thermophilic bacteria, organisms that love heat, might flourish. But eventually, the heat becomes too intense for even heat-adapted organisms.
Forests die.
Grasslands disappear. Insects, which are incredibly sensitive to temperature changes, might be among the first groups to go extinct. Without insects, plants lose their pollinators. The flowering plant kingdom collapses. Without plants, animals lose their food source. Animals starve or desperately flee to wherever it's cooler. The migrations are frantic. Life tries to move toward the poles, but even the poles are becoming too hot. Life tries to move to higher elevations, but the mountains become too hot. Life retreats into caves, into subsurface environments, into deep oceans where it might be cooler. But everywhere, the temperature is rising. Eventually, even the subsurface becomes uninhabitable. The heat penetrates everywhere. The water is gone or almost gone. The chemistry of life becomes impossible. Even extremophile organisms, organisms that can survive in extreme conditions, have their limits. The entire biosphere, billions of years old, containing millions of species, is extinguished. Not in a dramatic impact or explosion. Not in a sudden catastrophe that kills everything in hours or days. But through a slow, relentless increase in temperature and loss of water. The biosphere fades away. Species go extinct. Populations dwindle. And finally, there is nothing. Earth becomes a dead world. A sterile world. Just rock, dust, and a thick atmosphere. No water. No life. No possibility of life for billions of years into the future. But the story doesn't end there. The sun continues to get brighter. The planet continues to heat. And new processes become important. With no oceans, there's no water cycle to regulate temperature. The temperature variations between day and night become extreme. Without the buffering effect of oceans, which store heat and cool slowly, day and night temperatures can swing wildly. The poles might actually become cold enough for some CO2 to condense into dry ice at night, but the equator becomes an absolute furnace. The rock itself begins to change. At these extreme temperatures, minerals undergo chemical reactions. Volatile compounds, compounds that can vaporize, begin to escape from the rock into the atmosphere. Water that was locked away in hydrous minerals vaporizes. Carbon dioxide that was locked away in carbonates is released. The atmosphere becomes denser and more complex, with constituents that would be toxic to any conceivable life form. Some scientists have modeled the surface chemistry of this future, dead Earth. The picture is one of increasing chemical complexity as reactions that don't normally occur on cool planets become possible. But it's a complexity without life. It's the chemistry of a dead world. 2 billion years from now, the sun will be roughly 20% brighter than today. By 3 billion years from now, it will be 30% brighter. The planet continues to heat. The surface temperature might reach 400, 500, 600 degrees Fahrenheit. At these temperatures, lead melts. At these temperatures, the rocks themselves begin to glow red hot. The atmosphere becomes supercritical, so hot and so dense that it transcends the distinction between liquid and gas. It's neither liquid nor gas, but some exotic phase of matter. The atmospheric pressure at the surface might be dozens or hundreds of times greater than Earth's atmospheric pressure today. 5 billion years from now, as the sun approaches the red giant phase, something dramatic happens. The sun expands. its radius grows. It becomes hundreds of times larger than it is today. Its surface temperature decreases, but its total power output increases dramatically. The sun becomes a red giant. The expanded sun's atmosphere extends far beyond its current radius. It engulfs the innermost planets. It might engulf Mercury. It might engulf Venus. It might engulf Earth itself. Or Earth might orbit just barely outside the sun's atmosphere, its surface being slowly vaporized by the intense radiation. Either way, Earth as we know it is completely destroyed. It's not just uninhabitable, it's destroyed. The planet itself is torn apart by gravitational forces or evaporated by radiation. But this is all billions of years away, long after Earth has already become a dead world and humanity, if we're still around, has moved to other star systems. Now, let's think about what this all means for human civilization. We have roughly 1 billion years to figure out how to leave Earth and establish ourselves on other worlds. That's the timeline. That's our window. 1 billion years is incomprehensibly long. In 1 billion years, the universe will change profoundly. Stars will age. Galaxies will collide. New stars will form. Planets will drift through space. The cosmic background radiation will cool further. The universe itself will age by 7% of its current age. But for practical purposes, 1 billion years is our deadline. After that, Earth is no longer an option. Life cannot exist here. Humans cannot survive on the surface. Even building habitats and living underground would become impossible if the planet is too hot and the atmosphere is too thick. So what does that mean for human civilization? It means that the long-term goal of human civilization must be to become a spacefaring species. Not for adventure or discovery, though those are worthy goals. Not for economic resources or materials, though space has plenty of both. But for survival. We need to establish permanent human settlements on other worlds. We need to create independent, self-sustaining civilizations that don't depend on Earth. We need to spread out into the solar system and eventually to other star systems. Mars is the obvious first step. Mars is close by cosmic standards. It's about 54 million miles away at closest approach, though the distance varies depending on where Earth and Mars are in their orbits. Mars is a terrestrial planet, relatively similar to Earth in composition and structure, though much smaller and colder. The atmosphere is thin, only about 1% as dense as Earth's atmosphere, and it's mostly carbon dioxide. There's no liquid water on the surface today, though there is water ice at the poles, and frozen water in the subsurface. But these are engineering problems, not fundamental problems. They can be solved with sufficient technology and resources. Building a permanent human settlement on Mars is achievable with technology that we already have or can develop in the near term. It would require significant resources and engineering, but it's not impossible. Not like some of the more speculative ideas of moving planets or engineering stars. A Mars settlement would need to be self-sufficient in food production, energy generation, and water. Greenhouses would grow food using hydroponic systems where possible, or regolith, the Martian soil, amended with nutrients. Solar panels or nuclear reactors would generate power. Water ice would be melted for drinking and for oxygen generation. These are not trivial challenges. Growing food indoors at large scales has never been done. Generating enough power for a permanent settlement on Mars is challenging. Extracting water from ice and storing it is complex. But they're solvable problems. We have the physics. We have the engineering know-how. What we lack is the commitment and the resources. If we decided as a civilization that establishing permanent human settlements on Mars was a priority, we could do it. Once humans establish themselves on Mars, the next logical step would be the moons of the outer planets. Titan has a thick atmosphere and interesting chemistry. Europa has a subsurface ocean that might contain more water than all of Earth's oceans combined. Enceladus has water and organic compounds. These are harder to reach and harder to settle, but they're potentially valuable in the long term. Eventually, humans could establish space habitats, artificial worlds built in space, with their own gravity generated through rotation. These habitats could be positioned at stable points in the solar system or could orbit planets. They could have whatever environment humans want. Earth-like climates, exotic ecosystems, harsh environments for specialized industries. As the sun ages and Mars becomes too hot, thousands or millions of years from now, humans could retreat to the outer solar system. The moons of Jupiter and Saturn receive much less solar radiation than Earth or Mars, so they'll remain relatively cool as the sun brightens. Humans could live there for millions of years while continuously moving outward as the sun gets hotter. Eventually, as the sun approaches the red giant phase, humanity would need to leave the solar system entirely. This is where it gets truly speculative. How do you travel between star systems? How long does it take? How do you maintain a civilization over the timescales required for interstellar travel? There are proposals for generation ships, spacecraft designed to be self-sustaining for centuries or millennia, carrying human civilization to other stars. There are proposals for suspended animation or cryogenic preservation, allowing humans to sleep through the journey. There are proposals for artificial intelligence or robotic craft that could establish a foothold at another star before humans arrive. None of these are practical with current technology, but technology changes. 1 billion years is enough time for human civilization to figure out interstellar travel if it's at all possible within the laws of physics. The key is commitment. The key is recognizing that this is what we need to do. The key is investing in the research and development that will make it possible. Wait, some people ask, I thought the sun would just turn off in 5 billion years. Why is the timeline for Earth's destruction only 1 billion years? This is a great question, and the answer illuminates something important about stellar evolution. There's a difference between when the sun becomes too bright for Earth to support life, and when the sun actually runs out of fuel and undergoes its final dramatic transformation. The sun will be actively fusing hydrogen in its core for roughly 10 billion years total. About 4.5 billion years have already passed since the sun formed. That means roughly 5 to 5.5 billion years remain. So the 5 billion year figure is correct. The sun does have about 5 billion years of hydrogen left to fuse before the hydrogen in the core is depleted. But at the 5 billion year mark, the sun will have exhausted its hydrogen fuel. The hydrogen hasn't been completely fused, but the core becomes so depleted of hydrogen that the temperature and density drop below the threshold needed to sustain hydrogen fusion. At that point, something dramatic happens. The core will collapse and heat up. A different set of nuclear reactions will begin. The sun will balloon outward into what's called a red giant. This is a massive transformation in stellar structure and appearance. The sun will expand outward by a factor of hundreds. Its surface will cool slightly, falling from about 10,000 degrees Fahrenheit to maybe 4,000 degrees. But the total power output will increase dramatically. The sun will be much larger and much brighter than it is today. But Earth will become uninhabitable long before the red giant phase. It will become uninhabitable when the sun has brightened enough to trigger a runaway greenhouse effect. And the models suggest this will happen around 1 billion years from now, plus or minus a few hundred million years. That's only about 1/5 of the sun's remaining hydrogen-burning lifetime. That's much sooner than the dramatic red giant phase. So when we say the sun has 5 billion years left, we're talking about its remaining life as an active hydrogen-burning star. But Earth's habitability window closes much sooner, within the next billion years or so. Can we do anything to prevent this? Can we build a sunshade or some kind of technology to keep Earth cool as the sun gets brighter? The short answer is no, not in any practical sense. This is a consequence of the fundamental physics of stellar evolution. The sun is a star, and all stars evolve in basically the same way. Stars fuse hydrogen into helium. As they do, they get brighter. There's no way to prevent this. It's not a flaw in the sun. It's not something that could be fixed if we understood the sun better. It's the inevitable consequence of nuclear fusion and stellar structure. We could theoretically build a massive sunshade, a structure in space between the Earth and the sun that would block some of the solar radiation and keep Earth cool. Some scientists have even speculated about such mega-engineering projects. It's sometimes called a sunshade or a Dyson sphere or variations on those concepts. But such a structure would need to be planet-sized. The amount of material required would be incomprehensible. We're talking about material on the scale of thousands of kilometers in size. The engineering required would be beyond anything we can currently imagine. The energy required to build and maintain it would be astronomical, and I use that term literally. Moreover, once the sun becomes much hotter in a few billion years, even a huge sunshade wouldn't help. You'd need a sunshade that covers an increasingly larger area to block the increased radiation. The engineering challenges would grow exponentially. Eventually, it would become impossible. A sunshade is not a practical solution. The only practical response to the inevitable brightening of the sun is to accept that Earth has a finite habitable lifetime and to prepare for the long-term future of our species by developing the technology to leave Earth and settle other worlds. Should we care about this if it's a billion years away? Shouldn't we be focused on the climate crisis we're facing right now? The answer is yes to both. Yes, we should care about the long-term future of our species and the eventual uninhabitability of Earth due to solar evolution. Yes, we should also be focused on preventing human-caused climate change and preserving habitable conditions on Earth in the near term. These are not mutually exclusive goals. In fact, they reinforce each other. The same scientific and technological capabilities that allow us to understand and address human-caused climate change are the same capabilities that will eventually allow us to leave Earth and settle other worlds. Understanding that Earth has a finite habitable lifetime provides context and perspective on what our long-term goals should be as a species. It motivates investments in space exploration and technology development. It reminds us that we are not permanent residents of Earth and that our future lies beyond this planet. But understanding this should not distract us from the urgent problems we face today. Climate change caused by human activity is a problem we need to solve now, in the next few decades. The long-term problem of stellar evolution is a problem for future generations, for humans thousands or millions of years from now. Both are important. They operate on different timescales and require different solutions. But they're both real and they're both worth taking seriously. To understand how scientists predict Earth's climate in the distant future, it's useful to know a bit about climate modeling. This is cutting-edge science involving some of the most powerful computers on the planet. A climate model is a mathematical representation of Earth's physical systems. It includes the atmosphere, the oceans, the land surface, and the ice. It represents how these systems interact with each other. The basic principle is to divide the planet into a three-dimensional grid. Each cell in the grid represents a small region of Earth's surface and atmosphere. The grid might have cells that are tens of kilometers on a side and hundreds of meters in vertical thickness. For each cell, the model calculates properties like temperature, pressure, humidity, wind speed, and many other variables. The model uses the laws of physics to calculate how these variables change over time. For instance, if a cell is warmer than the surrounding cells, heat will flow out of that cell. If there's a pressure difference between cells, wind will blow from high pressure to low pressure. The model also includes processes that operate at smaller scales. Clouds form in individual cells based on the temperature and humidity. Precipitation falls. Ocean currents move heat around. Sea ice forms and melts. All of these processes are represented in the model, often with significant simplification because computers aren't powerful enough to model everything in complete detail. The model runs forward in time, calculating how Earth's climate evolves. A simulation might run for hours or days of computer time to simulate 10 years of real Earth time. To simulate 1,000,000 years, you need enormous computing power. To simulate 1 billion years, researchers typically run simulations of progressively larger time steps rather than simulating every year in detail. Moreover, the model includes coupling to stellar evolution models. As the sun's luminosity increases, the solar constant, the amount of solar energy reaching Earth, increases. This changed solar constant is the boundary condition that drives the climate change. Scientists run multiple simulations with slightly different parameters to understand the sensitivity of the results. They vary things like the concentration of carbon dioxide in the atmosphere, the properties of clouds, the properties of ice, the feedback parameters, and other assumptions. Different assumptions about these things lead to different predictions. The results are generally consistent across different modeling groups. Different teams of scientists using different models with different assumptions reach similar conclusions about when Earth will become uninhabitable. This gives confidence that the results are robust, that we're not just seeing artifacts of a particular model or a particular set of assumptions. The exact timeline varies. Some models predict that Earth becomes uninhabitable around 700 million years from now. Others predict 1 billion years. Others predict 1.2 billion years. The uncertainty is substantial, but not enormous. The range is roughly 700 million to 1.5 billion years. The most likely value seems to be around 1 billion years. This variation comes from uncertainty about how the carbon cycle will evolve over millions of years, how clouds will respond to extreme warming, how ice sheets will behave, and other factors. These are real uncertainties. Climate modeling is not perfect, but the models are good enough that we can make predictions with rough accuracy. Our galaxy, the Milky Way, contains about 200 billion stars. Of those, many are sun-like stars with planetary systems. Based on exoplanet surveys conducted over the past 20 years, we know that planets are common. Most stars have at least one planet. Many have multiple planets. A significant fraction of those planets are potentially Earth-like, meaning they're rocky planets of similar size to Earth, and potentially habitable, meaning they're in the habitable zone of their star where liquid water could exist on the surface. If we use conservative estimates, there might be billions of potentially habitable planets in our galaxy. Billions. But if the habitable zone window is only a few billion years, and if intelligent life takes billions of years to develop, then most of those planets never develop intelligent life. They might have simple microbial life for billions of years. But intelligent civilizations are rare. Very rare. Some scientists have tried to estimate the number of intelligent civilizations in the galaxy using the Drake equation. The Drake equation is a famous formula that attempts to estimate the number of intelligent civilizations in the galaxy. It multiplies together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of planets in the habitable zone, the fraction of habitable planets where life emerges, the fraction where intelligent life emerges, and so on. Different scientists have different estimates for these factors. Some are optimistic and suggest that intelligent life should be common. Others are pessimistic and suggest that intelligent life is very rare. The estimates vary wildly. Some scientists estimate there might be thousands of civilizations in the galaxy. Others estimate there might be only a handful. Still others estimate the number might be 0 or 1. But here's something that's been clarified by recent research. If intelligent civilizations are rare, and if they arise on planets that only have a limited habitable window, then most intelligent civilizations probably go extinct before they can establish themselves on other worlds. An intelligent civilization needs time to develop technology, to explore space, to establish settlements on other worlds. If a civilization has only a few billion years before their star becomes uninhabitable, they need to move fast. They need to leave their home planet and establish themselves elsewhere within a billion years or so. Otherwise, they go extinct with their home planet. This suggests that most intelligent civilizations in the galaxy are probably extinct. They emerged, they developed, they flourished, they created art and music and literature. But they failed to leave their home planets before those planets became uninhabitable. They're gone. Only a tiny fraction of intelligent civilizations, those that succeeded in establishing themselves on multiple worlds and eventually among the stars, might still exist. This is both humbling and inspiring. It's humbling because it suggests that even intelligence is not a guarantee of survival. A civilization can be intelligent, can have all the knowledge they need to leave their planet, and still go extinct if they don't act in time or if they fail in their attempts. It's inspiring because it means that if we succeed, if humanity becomes a spacefaring civilization, we'll be joining a very exclusive club. The rare civilizations that survived. The rare species that made it to the stars. That would be an extraordinary achievement. So we come to the conclusion of this exploration. We've covered a lot of ground. We've talked about stellar evolution and climate science, about the distant future of Earth and humanity, about the paradoxes and wonders of our place in the cosmos. Let me summarize the key takeaways because I want to make sure the message is clear. First, the sun is getting brighter. This is certain. It's not a hypothesis. It's not a theory that we're testing. It's a consequence of nuclear fusion and stellar evolution. is something we've understood for decades. It's not something that will change or go away. It's as certain as gravity. Second, Earth will become uninhabitable in roughly 1 billion years. This is very likely based on climate models and our understanding of planetary physics. There's uncertainty in the exact timeline. It could be 700 million years or 1.5 billion years, but it will happen within the next billion years. After that, Earth is no longer habitable. Life cannot exist here. Not complex life. Not even simple life. Third, we have time. 1 billion years is enough time to develop the technology to leave Earth and establish human civilization on other worlds. It's enough time to become a spacefaring species, to spread across the solar system, and eventually to reach other stars. That's not just enough time. That's an enormous amount of time. In 1 billion years, human technology will transform beyond anything we can currently imagine. Fourth, the long-term survival of humanity depends on leaving Earth. Not in the next decade or century, but eventually. We need to establish the goal of becoming a spacefaring species and commit to that goal. We need to invest in the research and development that will make this possible. Fifth, this is not instead of preserving Earth and addressing climate change today. We need to do both. We need to preserve Earth as our home in the near term, and we need to work toward leaving Earth in the long term. Both are important. Both require serious effort and serious investment. The sun will destroy Earth. This is not pessimism. This is not gloom and doom. This is simply the law of physics. This is what happens to planets as their stars age. But the destruction of Earth does not have to mean the destruction of humanity. If we're wise, if we're committed, if we understand the challenge and work toward solutions, we can ensure that humanity survives long beyond Earth. We can ensure that human civilization continues for billions of years. We can ensure that consciousness and intelligence persists in the universe, at least for a time. That's the goal. That's the challenge. That's the story that defines human civilization for the next billion years. The question now is, are you ready to be part of that story? Are you ready to live in a civilization that understands its place in the cosmos and works toward a long-term future? Are you ready to support the investments in science and technology that will make this possible? I believe the answer is yes. I believe that humanity is capable of rising to this challenge. I believe that we have the intelligence, the determination, and the resources to do this. But only if we choose to. Only if we make it a priority. Only if we recognize that the alternative, to remain confined to Earth and be destroyed when Earth becomes uninhabitable, is unacceptable. The sun will destroy Earth, but it doesn't have to destroy humanity. The future is ours to make. Let's make it a future where human civilization thrives for billions of years among the stars. What you've just heard is not speculation. It's not science fiction. It's the most recent understanding of planetary science, stellar astrophysics, and climate science. Yes, there are uncertainties. Yes, new research might change the details. But the broad strokes are clear. The sun will get brighter. Earth will warm. The oceans will evaporate. Life will die. This will happen. But that doesn't have to be the end of the story. That doesn't have to be humanity's fate. We have the time, the intelligence, and the capability to leave Earth and establish ourselves among the stars. All we need is the will. That's the message of this exploration. That's the call to action. The sun will destroy Earth, but humanity will survive. The future awaits.